talking about what is Retpoline. And if you're familiar with the Spectre Meltdown attacks that came out 2 years ago, we're going to be specifically focusing on the Spectre variant of those attacks. So really the objective of what we're going to try to achieve here today is we need to control how the CPU guesses what it's doing. So one way to view this is if you've got, this magic game where you would put a ball in a cup and you'd shuffle them around with the person's eyes closed, they open it up, and then, what cup is the ball under? Our goal is to ensure that one of those cups is always clear so that the CPU guessing will always know exactly where the ball is. That's really what we're trying to achieve here. Is Retpoline is trying to make this glass clear and forcing us to always get the answer right, or at least the answer we want to be right. There's a pretty general audience for this presentation, so I'm going to actually start this off with a little bit of a review of some computer architectures, sort of like 101. So if you're not familiar with assembly or coding, hopefully the background I provide will provide enough information so that you can kind of follow the rest of the presentation. From there, I'll briefly mention what the problem is, although we're not going to go into the actual specifics for a real Spectre attack. There's a lot more that needs to be discussed above and beyond just Retpoline, but we can briefly mention sort of what the issues are and then jump right into, from there, what Retpoline is. We'll do an actual in-depth description of the different Retpoline sequences, and then from there we'll finish with some of the disadvantages and take questions. So to kind of go over some of the background here to help make the presentation make a little bit more sense later on, I'd like to start with just discussing the instruction stream. So the instruction stream, if we look at the CPU in its most basic form, the CPU is designed to move through memory and execute one instruction after another. So it just does steps. And in real life, CPUs do not work this way. They're way more complicated than this. But for the sake of starting this thing off, let's just view the CPU as this thing that needs to move through memory and execute one instruction after another as a series of steps. One of these instructions is something called the jump instruction. The whole point of the jump instruction is that if the CPU is just executing one instruction after another, at some point it might want to jump to a completely random location in memory and start execution from there. It might jump down, it might jump up. For example, if it jumps down, that sometimes could be used to call a function, or if I jump back up, that's usually how we create loops. There's also different reasons why we might want to jump, but the point is that instead of it just being perfectly linear through the entire execution of a program, it's going to execute somewhere else in memory and continue execution from that point. It's also important to note that in this particular example, I'm showing that the address is encoded with the jump instruction. So what this means is that the actual address of where it's going to jump is known. We know it because it's actually embedded inside the instruction. Another type of instruction I like to talk about is the call instruction. So like the jump instruction, the call instruction will jump to some location in memory and continue execution from there. But in addition to doing that, before it does that jump, it will push the location of the next instruction onto something we call the stack. The stack can be viewed very similarly as your stack of plates in your cabinet for eating food. You take a stack or a plate off, you use it, you clean it, you put the plate back. And if you have 4 people at the house, you pull 4 plates off, you use them. You might put 2 back because 2 other people haven't finished dinner yet, and eventually it moves up and down. But the whole point is you put something on top, you take it off. So we have something very similar to that on the computer. It's basically a place of memory that we can push things onto, and it keeps growing until we pop things off. So the call instruction, before it does its jump, it's going to push, so put a plate on top of the stack, the address of the next instruction. The return instruction is another type of jump. Unlike the call instruction and the jump instruction that has the address sort of encoded inside the instruction, the return instruction gets its address from that stack. So it's designed to work in tandem with call. So if you look at this, we would basically start with the call instruction, which is midway through this diagram I have here. And before it jumps to the top instruction at the top of taking that orange or that sort of yellowy orangish color, it's going to take the location of the next instruction and it's going to push that onto the stack. From there, it's going to jump to that first instruction at the top of the diagram and continue execution until it hits return. Return is going to pop that address off the stack that was put there and then return back to the next instruction, allowing this instruction stream to continue execution from the point of when the call was originally made. This is how we implement functions. There's actually two different types of jumps. There's something called a direct jump and an indirect jump. The jump and call that I had just previously talked about had the address hard-coded right into the instruction. So we know at the time when we compile the code exactly where in memory we want to jump. It's right there, very quick and easy for the CPU to get to. Sometimes, however, we want to jump to a location that we don't know at compile time. We only know after the program's been running for a while. And to do that, we get the address of where we're going to jump to from a register or from memory. The return instruction is an indirect jump. It doesn't know at compile time where to jump to. It gets the address from the stack. We can do the same thing with jump and call. We can get the address from memory somewhere, or we can get the address from a register. The important thing to note is that if you're direct jump or call, you know exactly where you want to jump to at the time when the code is compiled. And what that means is that the CPU can get access to that address very quickly. With a indirect jump, we don't know. And so we have to go ask a register. We have to go find it in memory. That takes the CPU a lot longer to go find that address. So that's the key thing here, is the amount of time it takes for the CPU to figure out where it's going to jump. All right, so the next part here is we're going to talk a little bit about the instruction pipeline. So at the beginning, I talked about how the instruction stream executes one instruction one after another. If we were to zoom in on how the CPU executes that single instruction, it actually has to do it in several steps. The first thing it's going to do is go get the instruction from memory. So it'll fetch it. From there, it'll probably decode the instruction to figure out what kind of instruction is it. Is it a jump or a call or a return or something else like an add or a move? Once it knows what kind of instruction it is, it then needs to go fetch the inputs. Every instruction has different inputs. The return instruction has an input from memory. The call and jump instruction might get it from a register. There's all sorts of different inputs that it has to go fetch. This step can be really quick, or it could take quite a while, depending on where the data is. Finally, once it has all the information it needs, it'll then execute the instruction. And then, depending on the instruction, it might save the results somewhere, maybe to a register or memory or whatever. The reality is that a real CPU, this instruction pipeline is a lot larger than this. But this is a pretty simple way of looking at it to start to kind of help explain the point that we're trying to get to. The issue with this is if we look at it from this point of view, when instruction number 1 is being decoded, so it's in step 2 that I have here in this diagram, the hardware for fetching the instruction and the hardware for getting the inputs and executing the instruction and saving the results, it's all dormant. It's not doing anything. And this is an issue because there's an inefficiency here. What if I could find some way to keep all of the hardware busy constantly? And so that's really what the instruction pipeline is. It's a mechanism that allows us to execute instructions in parallel and keep each one of those steps, those pieces of hardware inside this pipeline busy at all times. When instruction number 1 is being decoded, the CPU immediately starts to fetch instruction number 2. And when instruction number 1 is getting its inputs fetched, instruction number 2 is being decoded, and instruction number 3 is being fetched from memory. And this process continues. The idea is to parallelize so that each piece of hardware is being kept busy at all times by executing as much in parallel as possible. There is one really big problem with this, though. If I haven't completely executed instruction number 1, how do I know what instruction number 2 is? Right? In the diagram I had before, it's just the next instruction, right? So I just look at where I am in memory and I just increase by the size of the instruction, and that's the next instruction, and you just keep doing that. But what if instruction number 1 is a jump? How do I know that instruction number 2 is the next instruction right after instruction number 1 in memory, or if it's some other instruction somewhere else in memory where I have to jump to? That's where speculative execution comes in. This is a fancy name for basically saying that the CPU has to guess what that next instruction is. As soon as it sees something like a jump or a call or a return, and it doesn't know what the address is of where it needs to go immediately, so it's an indirect jump or call or return, not a direct. A direct, it has that address encoded right in the instruction. It can get to that data very quickly. No speculative execution is needed because it just knows where to go. But if I have to go get it from a register, or I have to go, even worse, get it from memory, that can take quite a while. And I don't want to stall the pipeline. I want to keep that pipeline as full as possible. So I'm going to instead, because I don't know exactly where I'm going to go, I'm going to guess. I'm going to say, you know what? I think it's going to go over here. If the CPU guesses correctly, then everything's good. The pipeline is full. Everybody, everything is happy, and it just continues on, and there's no issues. But if it guesses wrong, it has to undo all of the instructions it just executed because they're all wrong. And it could have manipulated memory. It could have touched the, other types of registers or other types of resources. So it has to actually undo that execution. Otherwise, the execution of the program is not going to be correct because it guessed wrong and it started executing a bunch of instructions it shouldn't have. So now that we know what speculative execution is, I want to revisit the call and return instruction just a little bit to help, kind of explain a little bit more about what these instructions are actually doing. So again, if we think about it with the description before, the call instruction jumps to somewhere in memory, but right beforehand, it takes the location or the address of the next instruction, which we call the return address, and it pushes it onto the stack. In addition, however, it actually also pushes that same return address onto something we call the return stack buffer, or on AMD, it's the return address stack, and ARM has its own name for it as well. The RSB is a stack that's directly inside the CPU that the CPU can access a lot faster than it can something like the stack in actual memory. You don't have direct access to it. It's a hidden stack that's used by the instructions, and it's solely there to aid in speculation. Every single time a call instruction is executed, it takes the return address and it pushes it not just on the stack, but on this RSB. Then when a return instruction is executed, the return instruction has to go through this pipeline, so it's got several different steps. As soon as the CPU knows it's dealing with a return instruction, it pops the return address off of the RSB and uses that to speculatively determine or guess where it's supposed to go next. Eventually, through the pipeline, the CPU will determine, once it pops the return address off the actual stack, that that's where it was supposed to go in the first place, and speculation was all good, and the guess was correct, and life is happy. Under normal execution, this happens all the time. It's a really effective speculative execution algorithm. It's a means by which the CPU can essentially cache what this value is going to be when it finally pops it off the stack to figure out what it's going to do. It's very effective. All right, so here's the problem with speculation. When the CPU makes a guess, it has to perfectly undo that execution if it guesses wrong. Well, in reality, that's not what happens. CPUs leave things behind. It's actually possible for a CPU to not completely undo the execution of certain instructions and still keep the state of the CPU such that the execution of the application is correct. But since the state is not completely undone, there's these sort of like side effects or these things that are left behind. If it just so happens that the CPU speculatively executes an instruction that happens to be operating on a secret, say a password or a crypto key or something like that, well, that password or crypto key might remain inside the CPU somewhere, and it's possible that an attacker could use a side channel attack to gain access to this secret. This is the Spectre Attack. Basically, you convince the CPU to speculatively execute an instruction that happens to operate on a secret. That secret makes it into the cache. You then use a side channel cache attack to read that out of the cache while it's still there. The execution of the program remains correct, but you were able to gain access to a secret you shouldn't have been able to access. That's as far as I want to take the description of the Spectre Attack, because would need a whole nother presentation to go over how the side channel attack actually works and how you pull that out and timing and all that. So we're not going to go over that, but it's just important to understand that if the CPU makes a guess and it guesses incorrectly, it leaves things behind. And so what we want to do is we need to find a way to force the CPU to guess our own code that doesn't have a secret in it. We want it to always guess a piece of software that we write that we have control of, and not something else that possibly could expose secret information to an attacker who happens to have a mechanism to read out that data. So this gets us to Retpoline. Retpoline stands for return and trampoline, and it can be pronounced two different ways: Retpoline or Retpoline. Retpoline because the last four letters are line, and Retpoline because it actually stands for return and trampoline, so trampoline, lean. Everybody I've worked with always calls it Retpoline, so that's what I call it, but I think Retpoline is just as viable, and I've seen other people use that too, so I think either one are perfectly acceptable. So if you're wondering, how do I pronounce that weird word? I don't think anybody actually agrees that it could be Retpoline or Retpoline. The goal of the Retpoline is specifically to control the CPU's speculative execution, such that it always speculatively executes benign logic instead of something that might expose a secret. Now, if you're familiar with this space, you might be asking, how does this apply to other types of jumps like far jumps or direct jumps? So far jumps and direct jumps both are not affected by this. For far jumps, the speculative execution engine will stop. It doesn't actually try to do speculative execution for those types of jumps. And for direct jumps, it doesn't need to, because it has the address of where it needs to jump to very early. And so it doesn't need to guess, because it just knows where it's supposed to go quick enough that there's no problems with the pipeline. All right, so from this point, we're going to get pretty technical. Our goal here is to work through two different Retpoline sequences. The first one is an indirect jump. So here on the left-hand side, line number 1, we have jump to address, and it says address in memory. That's what the square brackets are saying, is jump to this location in memory. So that is an indirect jump. We're going to convert this one line of assembly into this entire block on the right side. And so what was one instruction is now 7. Now I say 7, if you notice on the right side, it's actually 9 lines. It's because anything that has this colon at the end of it, like capture spec and setup target, it's just a label. It's not actually an instruction. It's just so I can determine a location. It's a trick we use in assembly. So really there's 7 instructions here. And we're going to go through this entire sequence. But the important thing to remember as we go through this is we're trying to emulate the execution of an indirect jump instruction using this entire block of code. So all this block of code has to do is implement the indirect jump, but do it in a way that doesn't expose secrets through speculative execution. So we're going to start this by calling setup target. So that's line 6. So really it's instruction number 7. When we make this call, it's a direct call, so no speculation is incurred. But remember what a call does. It jumps to some location in memory, but right beforehand, it pushes the address of the next instruction to the stack and to the RSB. Well, the return address is line 2, capture spec. Really, it's the address of pause, but we're going to just keep it simple here and say capture spec. So after call is executed, the stack and the RSB both contain the return address, which is capture spec. So if a return instruction is ever executed, it's going to come back to line 2 when it's done. So now that we've called setup target, we are now on this move instruction. I don't want to go into the details of exactly what move is, other than to say that what this instruction is doing is it's changing the value on the stack. Now, if you remember from the original set of calls, we're trying to jump to address. So what we're going to do is we're going to take that address that we want to jump to, and we're going to change the value on the stack. We're not going to push to the stack. We're going to take the value that was once capture spec, and we're going to change it to address. Now, when an return instruction is executed, it's not going to return to capture spec like it would have before. Now it's going to return to address. That, in effect, implements a jump. But the key thing here is this move to the stack doesn't change the RSB. Again, we don't have control of the RSB. That is a CPU-specific feature for speculative execution. That remains the same. So here's where the, we kind of split into multiple universes. So you can kind of view it like, Avengers, when there's that line and eventually it kind of splits off into two different areas. In one, timeline, the return instruction is going to pop the return address off the stack, which is now address, and it's going to jump to that address. So ultimately it goes off and jumps to the address we want it to, and it's going to continue execution the way we want it to. But remember, getting that value off the stack takes a long time. And so while the CPU is waiting to figure out where it's actually supposed to go, it's going to go to the RSB and determine where am I supposed to speculatively start my execution. So that's the other timeline. And that timeline is ultimately the first thing that actually happens. And so the very next thing the CPU starts to do is it starts to execute capture spec, because that was the value, the return address on the RSB. And that's where it's going to speculatively start to execute. This capture spec block, it executes this thing called pause and lfence, and then it does a jump back to capture spec. So again, in the very beginning, like I said, if I can jump anywhere, right? I can jump down or I can jump back up. And if I jump back up, I can use that to create a loop. So every single time it executes pause lfence, it jumps back up to pause and then does pause lfence again and then jumps back up and just keeps doing that. There's an infinite loop. So we've actually forced the speculative execution engine into this infinite loop that's going to essentially do nothing. It's very benign. I'm not going to explain what pause and lfence do other than to say that it's just an optimization to help the performance of this block. Eventually, the CPU is going to determine that address was actually on the stack and that it was wrong. It guessed wrong, right? The value of the RSB, which was used for its guess, is not the same value that was on the stack because I modified it. And so it's going to realize that I did everything wrong. And so it's going to have to backtrack all the instructions it executed, which were basically just a bunch of pause, lfence, and jump, which don't actually have any side effects, sort of. And it will be very easy for the CPU to kind of undo and move on. Specifically, the most important thing to understand here is that the actual code that was speculatively executed, we control. It's benign. There's no secrets in this. And so we have successfully forced the speculative execution engine to operate on something we want it to, while at the same time still implementing a jump. That return instruction on line 8 is the jump. We just had to tell it, where do we want you to jump to? And we did this in a way that controlled that speculative execution. There's a little bit of extra credit. This added int3. So we talked about this RSB algorithm that's used for speculative execution. There happens to be another that's called straight line speculation. The return instruction can execute as many speculative engines as it wants. Again, like I said before, the pipeline is actually pretty big. And so if it can fill that pipeline with as many things as it can, it might actually try to speculative execute not just what's on the RSB, but in a third timeline, it might try to speculatively execute the very next instruction after return. And so we could still have a potential issue here. Now, what's important is that line number 9 never actually gets executed in normal execution, right? So it starts off with line 1, jumps down to line 6, and eventually when it hits line 8, which is return, that jumps to the location we actually want to go to, and it never actually executes this line 9. The speculative execution engine for RSB jumps out the capture spec and gets caught in this endless loop, so it also never goes to line 9. So the only way that you can get to line 9 is if straight line speculation attempts to try to execute that instruction. Since we want to control that, the way we do that is we add in an int3. Int3, once it sees that, it'll stop speculation. So this is just there to prevent yet another form of speculative execution that might crop up. All right, so now that we're done with the jump instruction, let's talk about the indirect call Retpoline sequence. So again, what does the call instruction do? It jumps to somewhere in memory, and then beforehand, it pushes the return address to the stack in the RSB. Well, we already know how to do the jump portion of this. We just did it. So we just have to find a way to put the return address onto the stack and onto the RSB. We can do the stack part pretty easy. We just showed that in the jump part. We could modify the stack to whatever value we want. But we don't have direct control of the RSB. That's controlled by the call instruction. So for me to be able to push something onto the RSB, I have to make a call. So the difference here is if I used a indirect call, I'd have a problem because of speculation. So instead, I need to find a way to convert this call instruction into a direct call. So the way we're going to do this is, again, remember, and we'll just sort of rephrase this. We're trying to take instruction number 1 on the left side and replace it with all of the instructions on the right side, 1 through 13. Instruction 2 and 14 are the same thing. That's next instruction. So that's where we're supposed to execute after the call instruction is done and the CPU sees a subsequent return. It's supposed to come back to this next instruction thing. So we start off with a jump, and that jump jumps all the way to the bottom of this block of code. From there, we call a direct, we make a call to a direct call. Again, that's not going to invoke speculation, but the call instruction will push the return address onto the stack, and it will push the return address onto the RSB. So we've succeeded in taking the address of the next instruction and pushing it onto the stack in RSB. Now, all we need to do is somehow execute our jump Retpoline, and we've successfully implemented the entire call instruction as well. And again, the way this does this is call jumps to line 2, and then from there, the rest of that stuff that's in there is the jump Retpoline. So we've successfully implemented the call, the indirect call. So this is how this works. Throughout this entire presentation, I have talked about indirect Retpolines. Sorry, inline Retpolines. So what that means is I've taken the address, I've taken the individual instruction, so call address here, and I've replaced it in the actual code with 13 new lines. Well, if I have a lot of call instructions or a lot of jumps that are all indirect, I'm ballooning the size of my code by a lot, right? Every single time you see one of these instructions, you got to add 13 more. I mean, that's horrible. So there's another form of these called out-of-line Retpolines, which we're not going to go over here because I think we've already gone through quite a bit of technical stuff here. But if you were able to follow all this and you're still interested, you could Google out-of-line Retpolines, and it's what kernels and applications actually end up implementing in real life. The reason being is that they can take this entire block, put it somewhere in executable memory, and then they call the Retpoline sequence, and then it executes. And so that they don't need to do this Retpoline sequence, replace it for every single instruction in the code. They just have one block somewhere that just gets reused over and over and over again. And there's some benefits to this because, for example, the call version of this can be implemented slightly differently so that you're not adding any additional instructions. So if you're interested and you are looking for where Retpolines are implemented within the kernel, you're actually looking for something called an out-of-line Retpoline. Okay, so before we conclude, we should probably talk about what the disadvantages of this are. The obvious advantage is that this particular type of code sequence prevents speculative execution, which helps us deal with certain types of Spectre attacks. The way that it does that is it controls the way that that speculative execution is executed to ensure it's always executing our benign logic. The obvious first issue, which we kind of just touched on, is that there's an impact to the size of your application or kernel. Now, again, if you use out-of-line replines, you can reduce that overall impact to something that's frankly negligible. The other disadvantage is the impact to performance. Every single instruction that's an indirect call or indirect jump now has to execute 7 or 13 or whatever the totals are. Instructions is a lot, right? That's horrible. If you have a lot of them, say for example, you writing a C++ application and you're using polymorphism, well, the way that works is it implements a indirect calls through something called a vtable. And those are all done through indirect calls. And so we actually see a pretty big performance impact on C++ code that makes heavy use of polymorphism. It's because you've got a lot of these instructions and they're all having to jump to this repline sequence and execute this sort of very controlled logic. And that's a lot more instructions that it might have to execute instead of a single jump. There's also a less obvious issue to performance, and that is that the speculative execution engine is no longer able to optimize those indirect calls and jumps. Surprisingly, these algorithms that make guesses are very accurate. And if we force the CPU to execute our repliline sequence, we're forcing the speculative execution not to do its job and optimize. We're forcing it to implement this benign endless loop that ultimately it's going to realize it was never supposed to execute in the first place, and it's going to have to undo all that. So we're essentially introducing manually pipeline stalls into the CPU, and that ultimately is also hurting performance. So we're not just taking a performance hit from having to execute more instructions. We're also taking a performance hit because we're no longer doing speculative execution as efficiently. And with that, I'll take questions. Okay, so so Pat asked, what is the impact of performance? So we basically just kind of talked about that. But he also asked, how does this relate to Meltdown? So at the very beginning, I talked about how this addresses the Spectre variant of the sort of Spectre Meltdown style attacks that came out a couple years ago. And Meltdown leverages a similar type of issue where you essentially try to execute an instruction that would normally be denied by the CPU because it doesn't have privileges to do so. But in the time it takes for it to realize that it wasn't supposed to execute that instruction because it's denied, it doesn't have the privileges to do so, it still actually reads in values from the system and places it into these sort of areas in the CPU that can be attacked via a side channel attack. So the Meltdown attack specifically is user space trying to read kernel memory, which could be a direct map, and ultimately that would allow you to read pretty much everything on the system. But you would normally not have access to that, so when you try to make that read, the CPU would eventually be, return back an error saying you don't have privileges to do that. But between the time it took it to figure out that it didn't actually have privileges, it will have actually read that memory and placed the results in the cache, and then a side channel attack can be used to read that value out of the cache and get access to the secret. So that's how the Meltdown attack works. So one is based off of privileges, the other one is based off of speculative execution. And the mitigation for Meltdown was very different. It required basically kernels and hypervisors to make very large changes to the way they handled paging to ensure that an application couldn't leverage this type of attack to gain access to secrets. Any other questions? All right, so John Marsh asks, you say the CPU is convinced to operate speculatively on an instruction with a secret. I was under the impression that you don't really have that control and that the CPU operates on secret data quite frequently, and you just take your chances or keep trying to see if you can see a secret in the memory. There's different ways that you can control the way that the CPU will attempt to operate on that particular secret. So that certainly the way that you're describing can be done. Basically, you just keep, trying to read and see if you find something that's useful. Maybe it's a secret, maybe it's garbage. But there are other ways to actually convince the CPU to execute logic that you want to. That's what all the different variations of Spectre are different ways in which you can convince the CPU to do what you want it to do instead of what it was going to do in the first place. So they're basically both are right. You can kind of do either one. All right. Well, I think that's it. Thank you very much. Oh, wait a minute. We got 2 additional questions. Let me address those before we conclude. So one of the questions was, would this only work as system-wide solution, or can it be selectively applied? It absolutely can be selectively applied, and that's exactly how it's done today. If you're, for example, running a C++ application that's not operating on a bunch of secrets, you probably aren't turning Retpoline on in your compilation, especially if you're implementing polymorphism. It's like, for example, my personal system has Retpoline enabled thanks to Windows, and there's applications that run in there that are manipulating keys and all that, and they all have Retpoline turned on. But my video game doesn't, and it absolutely is using polymorphism in C++. So it's not taking that performance hit. So yes, you can absolutely apply this on a per application basis. With the exception of the kernel is going to do it everywhere. And a hypervisor for that matter. And John said, thanks. Have you heard of the Google JavaScript? And the answer is no, I haven't. But now I'm going to go look that up. Another question was, any conditions config that would help hurt the effectiveness? So with respect to how it's configured, well, yeah, I mean, out-of-line replines can have somewhat of a performance impact due to the fact that you had to include them in the first place. So like, for example, the Linux kernel, even if you have a system that has mitigations for this built into hardware, the Linux kernel can detect that, or, Windows, it doesn't matter the kernel, but your kernel can detect that. And once it knows that, it can turn around and say, okay, well, I don't want to use Retpolines because I don't need to anymore because the hardware isn't vulnerable to this type of attack. But the problem is that the code, unless it's doing self-modifying code, it needs to know what to do. So ultimately, the way they use this is with these out-of-line Retpolines, they can actually jump to a different type of Retpoline that implements that Retpoline differently. And with basically, it doesn't implement a Retpoline. But there was still an additional instruction or two that was added as a result of that. So ultimately, even on systems that have hardware mitigations, there was a performance impact for having to deal with this across the board. It's just nowhere near as bad as it was when the when you have Retpoline completely turned on and using that whole sequence. Bruce asked, how does Intel HyperThreading affect mitigation strategies for Spectre? That's a fun one. That's a giant can of worms. So for example, there's another type of attack called MDS that really mucks around with this. There's also L1TF, which specifically addresses the L1 cache. HyperThreading has this unique issue where, so it made me just explain what HyperThreading is here for a second. Each CPU core is actually capable of executing more than one thread. And the way that that's done mostly, there's some dedicated hardware for threads, but in general, the way this is mostly done is through out-of-order execution in the instruction pipeline. And because it's the same actual physical core, it shares the same L1 cache. So all of the hyperthreads are executing with the same L1 cache. With that said, these types of attacks now become affected because the way that you might gain access to these secrets might be specific to that L1 cache and not, say, the L2 or L3, which at times can be easier to control. For example, from like a hypervisor point of view, it's such an issue that we actually have an MSR that we can flip that allows us to actually clear the L1 cache on all world switches, specifically because there's this problem. But there are a whole subset of different types of attacks that are geared around this sort of L1 cache and hyperthreading. And the L1TF is a fantastic example of that. That was essentially geared towards EPT on the hypervisor side. And then, of course, you have these other styles of attacks called MDS, which really actually touch the internal registers of the instruction pipeline. And honestly, to mitigate a lot of these types of things, some people have tried to implement what's called a core scheduler. So they try to make sure that threads that are executing on the CPU are always of the same application or virtual machine. And so you try to basically pair up multiple threads for the same application or same VM on the same core, so that if they were to try and leak data, they're just leaking data to themselves. So there's really no issue there. But in practice, the core schedulers, they oftentimes end up performing worse than if you just turned hyperthreading off. So in general, if you're concerned about these types of attacks, you're better off just turning hyperthreading off in practice.